Swayam Prabha. Digital India. Educated India.
Let us move on to the next problem. The major product formed in the following reaction. So here there is a alpha beta unsaturated ester is given. It's a cinnamate ester. This is treated with catalyst, osmium catalyst, 1 mole%, and dihydroquinone pol is the ligand that is used, and sulfonamine and potassium ferricyanide are the reagents that are used in this particular reaction. We end up with a product, and we have to identify what is the product that will be formed in this particular reaction. So here what the reaction actually takes place, if you look at A, B, C and D, we are actually getting a dihydroxide derivative, and we have to only look at what is the stereochemistry of the product that will be formed in this particular reaction. So this question was asked in June 2016. Let us look at how the reaction actually proceeds. So we have a trans, if you look at the starting material, we have a trans isomer, that is the starting material for our reaction. So this reaction is basically a dihydroxylation reaction that is carried out by the osmium tetroxide is generated in situ in this particular reaction in the presence of a co-oxidant. So potassium ferricyanide is used as a co-oxidant. In some reactions NMO is also used as a co-oxidant in many of these similar reactions. And the use of DHQ2 pol, which is called as the AD mix alpha reagent, that is the dihydroquinone, which is used as the ligand, is very crucial. So here this asymmetric AD is nothing but asymmetric dihydroxylation. Mix means that is the mixture that is used, and it gives the alpha isomer. So this is the main thing. Alpha means below the plane, so that is the only thing you have to remember. And this reaction, when we use DHQ2 pol as the ligand, that leads to dihydroxylation from the bottom phase. So that is the main thing we have to remember, and this gives a enantiomerically pure diol. So if we, then how do we know what is the bottom phase, what is the top phase? So to look at the, on the right hand side, we had actually drawn the small scheme like how we have to keep the molecule. So the molecule, the R group, the smallest one is kept at the top and the hydrogen is kept at the bottom corner. Then the large group is on your left bottom, and the second medium size alkyl or the whatever the substituent is kept on the right corner. So this way we actually spread the molecule in a square. Once you make this way, then we exactly know add AD alpha, that is DHQ, will give the dihydroxylation from the bottom phase, and if it is DHQD, then that will transfer the hydroxyl 2-hydroxyl group from the top. So that way we can easily find it out what is going to be the final product that will be formed. So here the reaction takes place from the alpha phase because we are using a DHQ as the ligand one, and then when we draw the molecule according to the structure given on the right hand side, we end up with a alpha phase, that is from the bottom phase of this alkene we will be this alpha beta unsaturated ester is drawn, and the product is formed as shown here, which can be translated into the product that is shown here. So phenyl is actually in this one showing at the bottom, but in the question answer we have the phenyl group which is actually at the top one. So that means the orientation or the molecule is exactly the mirror image of the one which is actually given here. So we have to just rotate the molecule in such a way that the phenyl group is actually at the top. So when we rotate that entire molecule like that, then this is the final product that we will get. And this reaction is called as the asymmetric, Sharp plus asymmetric dihydroxylation reaction. and Sharpless received Nobel Prize for this reaction. So epoxidation and asymmetric dihydroxylations are the reactions for which basically the introduction of oxygen units, that is what Nobel Prize was given to Sharpless in 2001. So this is one of the reaction, and this is a enantiomer. The products that are formed in many of these reactions are extreme enantiopurity, and many of these reactions are enantiospecific reactions. That means you will end up with only one of the product. By knowing the ligand what you are using, whether it is the epoxidation, whether it is a plus diethyl tartrate isomer or minus diethyl tartrate isomer, we can exactly say where the epoxidation will take place. Similarly, in the dihydroxylation reaction, if you use DHQ ligand or DHQD ligand, based on that you can also specifically say whether it is going to be the alpha phase dihydroxylation or beta phase dihydroxylation. So let us move on to the next problem. So here the major product formed in the reaction, following reaction is, we have a aldehyde as the starting material. So this is treated with the L-proline, acetone and DMSO as the first step. The second step, we have the acetoxyborohydrate reagent, and in the presence of acetic acid and methanol, acetonitrile at minus 40 degrees centigrade, the reaction is carried out. So this question was asked in December 2016. So when we treat proline with an aldehyde, so what is the reaction that will be formed? We have to know. So proline is an amino acid, so that has a amino group, and we have a aldehydic unit. So amine and aldehyde, when they both react, we can get two different types of product. One maybe imine is possible. In some cases enamine is also possible. So we will have to look at the reaction condition little bit carefully. So once we have an enamine, then how that is going to be reduced to give our final product. So that is the thing, and the enamine can be hydrolyzed later on to give the corresponding product. So how the reaction actually takes place is the formation of acetone and that amino acid L-proline leads to the formation of the enamine. So this is the enamine, because first we get to the imine, and the imine undergoes transfer of hydrogen to give the enamine. So this is the en unit, and this is the amine. So once the enamine is formed, the next step is the reaction with the corresponding aldehyde unit. So here we end up with the, as we already know how the electrophilic addition, this alkene will add to the carbonyl compound, because the lone pair of electron from the nitrogen is shifted between nitrogen and carbon bond, and this double bond becomes more nucleophilic, and then it can attack the electrophilic carbon. So that leads to the formation of this particular corresponding alcohol. So this is the first step that actually happens, and we have to do the second reaction also. So let us look at how the second reaction actually proceeds. So the keto alcohol is reduced by acetoxyborohydrate reagent. So there are two different ways the reduction can actually take place. So the first one is given at the top, the second one is also given at the bottom. So the carbonyl unit, which is supposed to undergo the reduction, is kept close to the hydride reagent. So here again the hydride. So the carbonyl unit is actually in the axial position in one of the intermediate transition state. In the other case, this is in the equatorial position. So these are all the two positions that are possible, and this is nothing but the Zimmermann-Traxler transition state. So in this particular case, only one is possible, the other one is not possible. So how do we know is very simply, like the top one is actually the favored position, and this one is not favored, because here the interactions are little bit higher, because we have a acetoxy unit here, and we have the R2, which is a bulky group, which actually prevents, due to that 1,3 diaxial interaction, this particular transition state is quite unstable, and that is the reason this is not favored. Here we do not have that particular interaction, and that is the reason this is actually favored in the top transition state. So that leads to 1,3-antidiol as the final product. So we can expect that this is going to be the final product that will be formed in this particular reduction, carbonyl reduction. Let us move on to the next problem. So here, the correct combination of reagents to effect the following transformation. We have a hydroxyaldehyde. That hydroxyaldehyde is converted to a diol. So this is the overall reaction that is happening. This question was asked in June 2017, and the major changes are the starting material has the hydroxy group pointing towards the observer, whereas in the final product the hydroxy group is away from the observer. So there is one change that is happening on the hydroxy unit. The second one, aldehyde is reduced to a primary alcohol. So a reduction also had happened, and here are the various combinations of the reagents that are given here. First one is POCl3 pyridine. So this is the first reagent that is used, then followed by silver acetate and lithium aluminum hydride. In the second one we have sodium borohydride and triphenyl phosphine and dead, and with benzoic acid as a esterifying acid. And in third one we have triphenyl phosphine dead and benzoic acid for the esterification reaction, followed by lithium aluminum hydride reduction. And the last one is PCC based oxidation and reduction by L-selectride. So these are all the things. So if we look at PCC, the PCC will actually oxidize the hydroxy compound to the ketone unit, and the L-selectride selectively reduces the carbonyl compound. So we can look at what are all the possible combinations that are happening, and based on that we will have to identify what is the reaction that is happening. So if we oxidize, if we look at the PCC L-selectride oxidation, if the carbonyl group is the hydroxyl is converted to a carbonyl unit and then it is reduced, we may end up with both isomers are possible. In other words, unless we use some chiral reagents, simple reduction will not give enantiomerically or even diastereomerically different compound, because if there is already some chiral center existing in the molecule, we end up with a diastereomeric product. If there is no chiral center existing, then we are going to end up with a enantiomer. So these are all the ways how a reduction may be possible in the presence of a asymmetric ligand or asymmetric catalyst. But L-selectride is not such thing. So that means the fourth combination is completely ruled out, because the reduction of alcohol, that means inversion of configuration of the alcohol, is not possible. And if we look at the second and third, we use triphenyl phosphine and dead and benzoic acid combination, which is nothing but a Michinobu reaction. So here inversion of configuration is possible. So either 2 or 3 may be possible. Only thing is, in the first case we have the sodium borohydride reduction. When we do the sodium borohydride reduction, what are we going to get? We are going to get a primary alcohol. So we have a primary alcohol. We also have a secondary alcohol. So that means there are 2 hydroxy units. When we have 2 hydroxy units, the dead reaction, that is the triphenyl phosphate Michinobu reaction, may happen at both the places. And in that case, we may get different types of products. So we only end up with the ester as the product and not the alcohol as a product. So that means 2 is also ruled out. So 2 also cannot be the possibility. And POCl3 pyridine maybe convert the hydroxy unit to a halo derivatives, and then what are the other reactions? They may not lead to the corresponding hydroxy derivative. So 1 is also ruled out. So from logically applying, we can easily figure it out. Most probably the condition 3 could be the right combination that is required or that may be used for this particular transformation. Let us look at what is the first step. The triphenyl phosphine and dead benzoic acid combination leads to the inversion of configuration. So that is possible. That will lead to a ester product, that is possible. So that means the hydroxy derivative is now inverted to the other isomer using the esterification, Mishnobu esterification reaction. Okay. Then the second step is lithium aluminum hydroxide based reduction. So lithium aluminum hydroxide will reduce both the aldehyde unit and the ester unit. So we may end up with the right product. So without even working out the problem, we can easily figure it out. It is going to be the C, that is the right one that is going to happen. Let us look at how the reaction actually proceeds. So in the first step, when we treat the secondary benzylic alcohol with benzoic acid and triphenyl phosphine diethyl azo dicarboxylate reagent, that leads to the inversion of the stereochemistry of the hydroxy carbon happens. So the hydroxy unit which is pointing towards the observer is now converted to the one which is pointing away from the observer. So we end up with the inverted ester, and the next step is reaction with the lithium aluminum hydride. This reduces both the ester and the aldehyde to the corresponding derivative. So this is a very clean and simple reaction which we can easily answer. Let us move on to the next problem. The major products A and B formed in the following reaction sequences. We have a allylic alcohol. This allylic alcohol is treated with Sharpless reagents. So what are all the reagents that are used? The moment we look at this DET, that is diethyl tartrate, then we can easily, and titanium isopropoxide. So this combination is generally used for the epoxidation, Sharpless epoxidation condition, and we have tertiary butyl hydroperoxide as the reagent. So that means this particular combination is mainly used for epoxidation reaction. So epoxidation of the allylic alcohol is the one that is possible. And then the next one is tertiary butyl thiol in the presence of sodium hydroxide gives a product B. So we have to find out what is A and B. So we have 1, 2, 3 and 4 combinations. So here we have intermediate A and B. And if you look at very carefully, what is the difference between all the 4 product is? All of them, the first intermediate A has the epoxide unit. Okay. The only difference is the stereochemistry is different for 2 sets of compound. And when we go to the final product B, the thioether is actually either internally or at the terminal is the only thing that is happening. So if you look at the stereochemistry is also different, whether it is pointing towards the observer or away from the observer. So these are all the different things. So here it is very difficult to predict what is going to be the product without actually working out the mechanism. So let us get into solving this problem. So the first one is nothing but the Sharpless epoxidation. So since we are using the plus isomer, we already know the epoxide is going to be the bottom face. The epoxide unit is going to be from the bottom face. So that is very easily we can fix the first one. And once the epoxide is formed, the next one is reaction with the sodium hydroxide. So the reaction with sodium hydroxide actually converts the hydrogen is removed and we end up with the oxide anion. So you have an oxide anion and there is a electrophilic site which can be easily opened by the nucleophilic anion. So what will happen? This internally attacks the epoxide and the epoxide actually, one of the epoxide opens up leading to the formation of another epoxide. So from which side it will attack? It is an SN2 attack. So that means the epoxide can only attack from the opposite side where the epoxide oxygen is present. So the oxide anion attacks from the top face and the epoxide opens up. So we end up with the epoxide as shown here. So this is the first step that will happen. And then the second step is the thiolate anion is going to attack. So it can attack at any place because of the bulky nature of the tertiary butyl group. The internal attack is not possible. So the thiolate anion will attack only from the external or the exterior site. So that is how the epoxide is actually opened up. and this epoxide opening leads to the final product as shown here. And with this we can easily figure it out what is our final product in this reaction. So the first one is the epoxidation, sharpless epoxidation using plus diethyl tartrate isomer, and the second one is intramolecular opening up of the epoxide. Okay, so these two are the crucial things that determines how the stereochemistry is going to be in the final product. And the simple opening up of the epoxide by the thiolate anion, because thiolate is a bulky group, so we end up with the thiolate anion adding to the terminal carbon. Let us move on to the next problem. So here the major product formed in the following reaction is this particular question was asked in the CSIR exam, but there is a small correction in the structure. The structure is actually in the question paper, the oxygen is actually missing. It may be a printing error. So this compound is basically called as N-propanol oxazolidone. Basically, Dieter Evans actually explored a lot about these particular oxazolidones, and his one of the paper exactly talks about this particular reaction. So here we have the oxazolidone derivative, a substituted oxazolidone derivative is there, and this is treated with boron triflate. So the first step is reaction with the boron triflate in the presence of a base triethylamine. The second step is reaction with the benzaldehyde. The last step is lithium hydroxide, hydrogen peroxide, and water combination. This is nothing but the hydrolysis reaction. Okay, so these are all the overall reactions. So these reactions leads to 4 type of product A, B, C, D are given here, and we have to find out what are the final product that is possible in this particular reaction. So the first step is nothing but the boron enolate reaction with this particular carbonyl compound. So the base triethylamine abstract the most acidic hydrogen atom, and that leads to the carboxylate oxide anion. So this oxide anion attacks the boron with the O triplet, that is the triplet ester group is lost. So all these things happen in the first step, and this reaction is a very specific reaction. This gives only the Z enolate, because Evans actually used lithium enolate for the same reaction, and he observed that lithium and enolate actually gives Z and E isomers in different ratios, but use of borane very specifically produces the Z isomer with the Z to E ratio greater than 99%. So this is a very crucial thing, because he published this work in JACS, and the use of boron enolate was very crucial for the formation of Z enolate. So this is the first step that is happening, and here see the stereoselective enolization leads to the required product. So once the cis enolate is actually formed, the next step is basically reaction with the aldehyde. So enolate addition with an aldehyde is nothing but an aldol reaction, so that many of you know. So here we end up with the erythro or the syn isomer that is formed in this particular reaction. This is obtained after the acidic workup, and once we have the Z isomer, how we get the Z isomer is actually given here in the Zimmermann-Traxler transition state. So here we can actually see the transfer of the hydroxyl, actually hydride ion takes place from the same side of the carbonyl group where we have. So here is our aldehydic unit that is present, and the hydride ion from the boron is actually transferred to this particular carbon. So this is the Zimmermann-Traxler transition state as shown here. So this is developed by Evans, and this system is actually called as Evans system, and this actually leads to the erythroselective chiral aldol condensation reaction, and we end up with the very specifically the erythro or the syn isomer as our final product. So once this erythro isomer is formed, then the next step is the hydrolysis using lithium hydroxide. So this does not cleave. This oxazolidone part is actually cleaved during the hydrolysis reaction. So that leads to the liberation of the carboxylic acid unit, and we end up with the final product as shown here. So this is the overall reaction in this particular case. So here these two groups are in the cis orientation or syn orientation.